A 200-gram ball travels towards a wall at 12 meters per second and rebounds at 8. It is tempting to say that momentum changes by 0.8 kilograms meters per second, the mass multiplied by the difference between the two speeds. But is that correct? Momentum is mass multiplied by velocity, p equals mv. Mass is a scalar, but velocity is a vector, so momentum is a vector too. The direction or sign is part of the answer. Take right as positive. Before impact, the ball is travelling left, so its velocity is minus 12 meters per second. Its initial momentum is 0.200 multiplied by minus 12, which is minus 2.4 kilogram meters per second. After impact, the ball travels right at 8.0 meters per second. Its final momentum is positive 1.6 kilogram meters per second. The change in momentum is final momentum minus initial momentum, so delta P is positive 1.6 minus negative 2.4, giving the positive 4.0 kilogram meters per second. It is not 0.8. The ball reverses direction, so its initial and final momentum vectors point in opposite directions. The positive change is towards the right. Newton's second law can be written in a form that connects force to this change. The resultant force on an object equals its rate of change of momentum. Over a measured interval, the average resultant force is the change of momentum divided by the time taken. The ball is in contact with the wall for 0.020 seconds. The average horizontal resultant force on the ball is therefore positive 4.0 divided by 0.020, i.e. positive 200 newtons. The sign tells us that the wall pushed the ball to the right. The net impulse on the ball comes from the resultant force acting over a time interval. For a constant resultant force, impulse equals F subscript resultant delta T. If the resultant force varies, its average value multiplied by the time interval gives the same net impulse. Net impulse equals the change in momentum. Here, 200 newtons multiplied by 0.020 seconds gives positive 4.0 newton seconds. 1 newton second is equivalent to 1 kilogram meters per second. So the units agree. For constant mass, this momentum form reduces to F subscript resultant equals ma. It is especially useful when a force acts for a short period of time and produces a sudden change in velocity. Impact force usually varies during contact, and real trace may be irregular. On a graph of horizontal resultant force against time, the signed area between the curve and the time axis is the net impulse. Here, model this collision with an idealized triangular pulse, 0.020 seconds wide. Its area must be positive 4.0 newton seconds. Area equals 1/2 times base times height, so the peak force is 400 newtons. But that is just the peak. The average force is still 200 newtons. Now, keep the ball's initial and final momenta the same, but double the contact time. The impulse, and therefore the graph area, must remain 4.0 newton seconds. Spread the same area across 0.040 seconds, and the average force halves to 100 newtons. For a similar triangular pulse, the peak also halves to 200 newtons. This one principle is behind padding, protective packaging, and the crumple zones on cars. For the same change in momentum, increasing the time reduces the average force. The qualification matters. If the final momentum changes, the impulse changes too. The method is simple. Choose a positive direction. Calculate P equals mv before and after. Find delta P as final minus initial. Then use impulse, average force, or the area under a force time graph. Momentum is a vector quantity determined by an object's mass and velocity. Impulse is the change in momentum produced by a resultant force acting over time. Next lesson, we're going to use the conservation of momentum to analyse collisions.